Hey everyone, welcome back to another video on CIE A Level Physics revision series. Today we're going to talk about the third subtopic of dynamics. Although you may see more contents listed than required in the syllabus, but understanding these key terms will help us quite a lot in dealing with principle of conservation of momentum and how do we solve questions for elastic or inelastic questions. So first off, total momentum, we are actually this is a no-brainer. Basically, it's the sum of momenta of interacting bodies. Even if they are not interacting or just a system of bodies that we are considering. So what that basically means is that you have two bodies, M1, you have another body, M2. They are going both of them in a single direction. So their total momentum would be just the sum of M1 U1 plus M2 U2. What about when one of them is moving in an opposite direction? So for example, this is same as before, U1 in this direction, but this one is moving towards it, U2. Now, just like before, we assign a positive direction. So U2 in that perspective would be negative. So total momentum would be M1 U1 plus M2 minus U2. So when you simplify this, this would become M1 U1 minus M2 U2. So the direction part over here is very important. And we will be dealing with total momentum before and after certain events, such as collisions. But finding or writing the total momentum would be based on these two examples. So wherever the direction is opposite, the momentum will be taken as negative because momentum itself is a vector quantity. Now, impulse. Impulse is basically just itself change in momentum. It is defined as change in momentum. So basically, the change in P, which if you remember from the definition of force, so force is equal to rate of change of momentum, this would be equal to force times by the duration of time the force is acting. So again, this would be a vector quantity also, because again, this is a change in momentum. So if momentum is a vector quantity, change in momentum would be a vector quantity also, and the units, it will have the same units as momentum, same units as momentum. So this can either be kg, meters per second, or as you can see over here, Newton second. So you can assign Newton second also. Either way, that's the same. Now, change in momentum, we already saw this. What that basically means is momentum after minus momentum initial. So we have to be very careful with the signs of V and U because we have to assign an arbitrary positive direction. So if U or V, either one of them is uh, in the negative direction, you will have to give it a negative sign. Next up is the concept of open closed systems and isolated systems. Although these are more important in thermodynamics, but just to give you an idea why we are talking about this, open systems are those where there is an exchange of mass and energy. And energy exchange can be in the form of work also. So in this case, why we're talking about this, we're talking about momentum. So obviously mass isn't conserved over here because mass exchange can happen. But external forces, what about the external forces? So external forces, since there is an exchange of energy and work, this could mean external forces, which just simply means forces other than the system, like other than the internal forces of the system. Then we have closed. No mass exchange, but energy can be exchanged. So no mass exchange, but work or energy can be exchanged. So again, we are talking about external forces or forces just in case. Isolated. Isolated system. This is the uh, important one, important to our discussion today. So no mass or energy exchange. So we want the system of bodies to be isolated, then that means we are not considering any mass exchange with the surroundings or surrounding environment, or there is no energy or work exchange. So in that case, no external forces will be acting on the system. Acting on the system. Again, this is an assumption, is assuming bodies are in an isolated system. However, what does this mean when we're talking about conservation of momentum? So if there are no external forces acting on the system, that means the total momentum can be conserved. Because there are no other forces acting on the system, no friction, no applied forces. So the total momentum, just like what we saw over here, total momentum of interacting bodies or system of bodies will remain the same after a certain event even. So for example, like a collision or something. In this one, only if external forces are not present. Like if the energy or the work exchange is not involving any external forces, and obviously no conservation of momentum. So this is the system that we are interested in. So the principle of conservation of momentum is based on the assumption that the system of bodies or the bodies that we are considering are isolated system, are a part of an isolated system, or there are no external forces acting on the system. So, principle of conservation of momentum can be written two ways. There are two parts for this. So one part is total momentum of interacting bodies is conserved. I'm going to add just a plus over here. This is a very important point. Provided no external forces act on system. Sorry. Yeah. So this is the assumption. So if there are no external forces acting on the system, then we can assume the principle of conservation of momentum. Other than this, you could also write, provided the system is isolated. So provided the system of interacting bodies is isolated. Now, either way, you can either write no external forces act on the system or the system is isolated. Either way, that's your choice. So, but only one of them is required. Even if you say isolated system, that would mean the same thing. Just show you that in the formulae and definitions booklet for AS, we have this written over here. So, so in both of these cases, okay. So principle of conservation of momentum states that total momentum of an isolated system is written in red, or no external forces act on the system. So this, you can choose your word, but the total momentum of the interacting bodies remains constant. So what that means is before and after a certain event. So total momentum before, we are mostly going to be working with collisions, so, and total momentum after collisions, or after the interaction, however you want to play it. So what that means is m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. Now, to understand how this actually comes, this is a consequence of Newton's third law and the change in momentum, basically. So Newton's third law we are already familiar with, that if two bodies are having an interaction with each other, so for example, this is A, this is B, this would be force B, this would be force A that A exerts on B. So we know that these two are in itself going to be the same. However, the force A is causing a change in momentum for B, and force B is causing a change in momentum for A. So let me write it this way. So FB equals to minus FA. Either way, it's going to be the same. So let's call it, this is, no, and B is fine. So this would be force B is causing a change in momentum for force A. So that means MA VA minus MA UA equals to minus force A is causing a change in momentum for B, simply MV minus MU. We already saw that above. So MV VB minus MB UB. So once you multiply the minus inside, this becomes minus MB VB plus MB UB. Now collecting all the terms on one side, so V terms on this side, so MAVA plus MB and U terms on one side, so MAUA plus MBUB. So whether it's body 1, body 2, M1U2 or AB form, this is how the principle of conservation of momentum is formed. So this is the after and this is the before. Either way, it means the same thing. And again, this also assumes that there are no other external forces acting on the system. Right, okay. Now, a concept called relative velocity. So, for example, if you have an object A that is going to this thing, this is object A, its velocity, let's say VA, is 5 meters per second. And there's an object B going in this direction. Let's say VB is equal to, let's say 10 meters per second. Now, since we're talking about relative velocity, we are going to be talking about velocity of one object with respect to another. So velocity of an object with respect to another. So nomenclature-wise, if we write AB, this is going to be velocity of object A with respect to B. So let's write it once. Velocity of object A with respect to B. Similarly, VBA would be opposite. Velocity of object B with respect to A. So the velocities that VA and VB are basically are from a stationary observer. So velocities from the perspective of a stationary observer or a fixed frame of reference. Fixed reference. Imagine yourself standing over here and watching these two collide with each other. So those will be the velocities from the stationary observer. But the relative velocity is from with respect to each other. So how do we actually do that? So for example, if we have VAB, its formula is going to be just simply VA minus V. And opposite way would be VB minus VA. Now, since the directions are opposite, we can designate one direction to be positive. So VB would be negative in that regard. So this would be 5 minus 10. So this would become 15 meters per second. And this one, basically, right, so VB now is minus 10 and VA is positive, and this is coming out to be minus 15 meters per second. So as you can see, as with vectors, these two are negatives of each other, which is not a coincidence because they are opposite vectors to each other. So what this basically means is, uh, from the perspective of B, because it is also moving, A is coming at B at 15 meters per second. Because it feels like, you can say it feels like to B that A is coming at it at 15 meters per second because it's not stationary. It is also moving. It is also moving closer to A. Same case is happening with A. Now, what if we include some angles in this? So, for example, let's say we have A going this way. Sorry, no. Same 5 meters per second. And I don't think we need the distance, the directions, or even the values. Let's call it VA. And let's say you have straight again this way, VB. Now, can you try to find out the relative velocity between the two? So VAB, again, the formula will be the same, but we will handle this using the directional way of handling the addition. So VA minus VB would be, so VA, this is your VA, and minus VB would be this. So the sum would appear to be, sorry, this. So this is your VA minus VB. So this means that from the perspective of B, A is moving this way. A is coming at B this way. Right, okay. So now I think we can go to the next thing, which is principle of conservation. Okay, we have actually already done that. We have done this. We have done this. Right, so let's talk about the principle of conservation of momentum in more detail. So what happens when the bodies are colliding? First things first, total momentum is always conserved. Total momentum is always conserved. This is going to be the case. However, kinetic energy may or may not be conserved. So we will discuss in which case it is conserved, which case it is not. So the case in which is conserved, those are called elastic collisions. CAIE conserved or EK conserved. And the ones in which kinetic energy is not conserved are called inelastic collisions. EK not conserved. So in this case over here, some energy is lost. So mathematically what this will look like, so in the case of elastic collisions, Total momentum is conserved. So total momentum, so you will have m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. And since kinetic energy is also conserved in elastic collision, so you will have half m u1 squared plus half m u2 squared equals to half m v1 squared plus half m v2 squared. Oh, sorry, m2 squared, m2, m1, m1. Now, in the case of inelastic collisions, so we still have change in moment, like momentum is still conserved. So m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2, but the kinetic energy is not conserved. So half m u1 squared plus half m2 u2 squared is not equal to half m1 v1 squared plus half m2 v2 squared. But this is not going to happen. Now, when you have perfectly elastic collisions, that mean everything is conserved, there's a special scenario over here. So I'll make some space for this. Perfectly elastic collisions. You can handle them separately also, if the question says that the certain collision is perfectly elastic. So perfectly elastic collision, as with elastic collisions, the kinetic energy is conserved, momentum is conserved, but relative speed, or you can say velocity also, basically. So what was that? Speed of approach is equal to relative, let me write it this way, is equal to relative speed of separation. What this means is that they're talking about the magnitude part, that the magnitude of relative speed of approach, you can also call it the relative speed of bodies before collision. Actually, I should have collision equals to relative speed of separation. And relative speed is the same concept we just talked about in this video, in the start of this video. So relative speed of after collision. So basically, if you have V1 minus V2, wait a second, U1 minus U2, or UA minus UB, this would have the same magnitude as V1 minus V2 and VA minus VB. This is about magnitude. But what about the direction? Directions are reversed. The relative velocity directions are reversed. So how we actually write this, like the full without the mod operator, is that the relative speed of approach is equal to negative of relative speed of separation. So you will have to pick one from one perspective, like with respect to which body. So for example, if you are selecting AB perspective, for example, AB, so UA minus UB, it will be negative of VA minus VB. Again, directions, you will have to take care of that. This will simplify to UA minus UB, VB minus VA. If you forget this one, this is easier to remember. The first one is easier to remember. Now, the cases for these are very important, especially the direction ones. So if objects have opposite directions, we actually saw this in the relative velocity case also. So if objects are moving with VA and this is your VB, it doesn't matter if it's the final velocity or initial velocity. So relative speed would be, like from one perspective, VAB, for example, this is going to be VA minus VB because they are colliding head on. But what if they have opposite, same direction? Objects have same direction. Now, this can go on, these cases can be used for before or after either way. So relative speed VAB would be VA minus VB because both of them will be having same direction. So VA is same direction, VB is in same direction. Now it doesn't matter what the speeds are, it would be the same. So speeds will be subtracted if they have the same direction, and if they have opposite directions, it will be added. But you don't have to remember that. You just have to remember this rule over here. Right. Okay. Now, common scenario that you might see is after collision, two bodies stick to each other. So when two bodies stick to each other, stick to each other. So how its conservation of momentum formula will look like, its masses will add up and the body will move off with a common velocity. So this is a case that comes up in many different forms. Maybe there's a bullet lodged in an object, maybe something else. All right, so let's look at some past paper questions to practice this concept. All right, so let's see questions. Okay. A disk of mass m is moving across a frictionless surface with constant velocity u. It collides with a stationary disk of mass for m. The diagram shows the view from above of the motion of two disks before and after the collision. What is the initial velocity u of the disk of mass m? Okay, so remember, conservation of momentum works in all dimensions. So if this motion is happening in 2 dimensions, we can make separate equations for x and y motions. So before collision, so before parallel to x-axis, you have total momentum. We are just considering total momentum first. So you have m times by u. Actually, we can just say mu and plus 0 because there is no y. There is 0 because there is no motion or no velocity of either of these objects that way. For after, there is in both the cases. So let's see the horizontal or the, sorry, x first, x components first. So velocity over here is 4 cos 45, but m also. And this would be v cos 45, but with 4m. So we have to be very careful with this. So this is going to be m times by 4 cos 45 plus, since it is in the same direction, 4m v cos 45. So this simplifies to 4m cos 45 plus 4m v cos 45. So basically you can say 4m cos 45 is common in both terms, but we can let it go for a minute. Now, parallel to, or the perpendicular to the motion, sorry, this is going to be 4 sine 45 meters per second, and this is v sine 45, but it's going to be considered opposite to positive direction. We are considering this to be positive and this to be positive. So parallel to y, this is going to be m times by 4 sine 45 plus 4m minus v sine 45. So this would lead to 4m sine 45 minus 4m v sine 45. Now, total momentum before and after. To find out u, we need to figure out what v is. And what we can do is if we equate these two equations. So this thing is equal to 0. So the y equation first. So you have 4m sine 45. Once you equate equal to 0, the other thing can go on this side, 4mv sine 45. So 4m gets cancelled, sine 45 gets cancelled. So v is 1. Now if v is 1, we can apply v on this thing. So now motion parallel to x, total momentum before is mu just simply. So mu equals to 4m cos 45. So 4m cos 45 plus 4. This now v is 1, so this is just going to be 4m cos 45 also. So m gets cancelled. Cos 45 is basically under root 2 over 2, and so is the sine 45. So u is 4 root 2 over 2 plus 4 root 2 over 2. So this becomes 4 root 2. So we just need to figure out what this value is. So 4 root 2. This is 5.6. So this value. All right. A moving object strikes a stationary object. The collision is inelastic. So remember, this means that EK not conserved. So objects move off together. Move off together means masses are m1 m2 times by v. This is the after case. Assume that the two objects form an isolated system. That means we can use principle of conservation of momentum, which shows the possible values of total momentum and total kinetic energy for the system before and after the collision. Okay, so first off, if the collision is elastic, kinetic energy is not conserved, so we need to see which one is possible. So before and after, obviously after cannot be greater, so after cannot be greater, and since this is an inelastic, so say same kinetic energy 1 discarded because 90 discarded, 30-90 will be discarded because after collision energy cannot increase. Now we have 90-30, 90-30 case, so we have to choose from one of them. Now we need to see which one is the total momentum before collision, total momentum after collision. Since this is an isolated system, we can use the total momentum before and after are equal. So C would be the right answer. Right. Okay. Two train carriages, each of mass 5,000 kg, roll towards one another on horizontal frictionless track. One is traveling at a speed of 2 meters per second and the other at the speed of 1 meters per second. They collide and join together. Again, that means that the momentum after is basically m1 plus m2 times by v. And what is the kinetic energy lost during the collision? What is the kinetic energy lost during the collision? They collide and join together. Okay, all right. So basically, we can find out the v. So u1 plus m2 u2 equals to m1 plus m2 times by v. We need to find out v first. So m1 is 5,000. Actually, both of them are 5,000. However, u1 is 2 if you take this direction to be positive. 1 would be taken as negative. And now m1 plus m2, that would become 10,000 and v. So this would become v. 2 minus 1 is v, 1, 5,000, what, 10,000. So 5,000 divided by 10,000 is basically 0.5 meters per second. So kinetic energy, now we need to see what's kinetic energy. So EK before is half. Again, masses are the same, so 5,000, and u squared plus v squared, and EK after is half. Masses are combined, so 10,000, and 0.5 whole square. So you just need to figure out the difference. So 0.5 times by 5,000 times by 4 plus 1, 5, minus 0.5 times by 10,000 times by 0.5 squared. So this is going to be, if you do it in the normal form, this would be 11250. So the difference between before and after. Okay, all right. Two objects x and y form an isolated system. That means you can use the principle of conservation of momentum. X and y collide and then separate. The mass of x is greater than mass of y. So mass of x is greater than mass of y. Which statement about the collision is correct? The change in momentum of y is greater than the change in momentum of x. No, this is not correct because we saw that F1 is going to be minus F2, which means that for the duration of this time, the change in momentum for object 1 is going to be the same as change in momentum for object 2, but directed opposite. This is the consequence of Newton's third law. So this is not going to be correct. The force on y is greater than the force x, definitely same point over here. Forces that x and y exert on each other act for the same length of time. This is correct. And the forces that x and y exert on each other, gravitational forces only, no. This is going to be C. Which row states whether total momentum and total kinetic energy are conserved in inelastic collision in which there are no external forces? So, inelastic, so that means kinetic energy not conserved. So kinetic energy conserved, these will cancel out, total momentum conserved, so B. So process of elimination can speed up the process very quickly. We've already done these. Okay. Sphere X and Y form an isolated system. Again, that means principle of conservation of momentum can be applied. Mass of Y is greater than the mass of X. Sphere Y is initially stationary, so Uy is 0. Sphere X collides elastically with sphere Y, which means that this is, what was it? Kinetic energy conserved. Sphere of X, speed of sphere of X before the collision is U. Which statement must be correct? Okay. Sphere X rebounds with a speed that is greater than the U, and sphere Y moves off with a speed that is less than U. It cannot rebound with a speed greater than U. This is an impossibility. Speed that is less than U, and sphere Y moves off with a speed that is also less than U. This is going to be the correct one. This is the only thing that makes sense. Right. Moving on. Collide inelastically, so total kinetic energy not conserved, reduced, total momentum conserved. C, same. I think it's the same question. Right. Okay. So this question is also repeated. I think you can see this in 2012 also. I've forgotten what variant was it. So a lead pellet is shot vertically upwards into a clay block that is stationary at the moment of impact, but is able to rise freely after the impact. The mass of the pellet is 5 grams and the mass of the clay block is 95 grams. The pellet hits the block with an initial velocity of 200 meters per second and it embeds itself in the block and does not emerge. That means after collision is m1 plus m2 v. So how high above its initial position will the block rise? So basically we need to find out the initial velocity after the collision. So basically we will use principle of conservation of momentum. So 5 grams times by speed 200 plus 0 because this is stationary. And now their masses are combined, so this is going to be 100 grams times by V, which we need to find out. So V would be 5 times by 200, 1000, times by 10 raised to power 3, which basically they cancel out, making it 1, and divided by 100 times by 10 raised to power 3, which is 0.1. So, so this is going to be just to, so this will turn out to be 10 basically. So just to make sure that we are correct, 5 times by 200 times by, we don't need to do 10 raised to power minus 3, and divided by 100, so this is 10. So 10 meters per second. Now this is the initial velocity u after collision is 10. We need to figure out what's the height covered. So 2as equals to v squared minus u squared. So at highest position v is going to be 0. So a is minus g. So you have 2 times by minus 9.81 times by h equals to minus 10 squared. So h would be 100 divided by 2 times by 9.81. So 100 divided by 2 divided by 9.81. So this is 5.1 meters. Okay. Okay. Which statement about the perfectly elastic collision between the two objects is correct? So relative speed of approach is equal to the relative speed of separation, and perfectly elastic, so total kinetic energy is conserved. So total kinetic energy is conserved. These two are correct. Relative speed of approach equals the relative speed of separation, so A is correct. Right. Okay. Two balls P and Q of equal mass move along a straight line directly towards each other as shown. Ball P has velocity 1.3 to the right. Ball Q has velocity 0.5 meters per second to the left. P and Q collide with one another. Collision is perfectly elastic, so that means we can use the relative speed equals to relative speed, and the total momentum is conserved. Which diagram shows the position of P and Q after the collision? And these are equal masses. So basically you have UP minus UQ, opposite directions, minus VP minus VQ. So this will add up to be UP minus UQ, VQ minus VP. So opposite direction, so UP is 1.3 minus 0.5 equals to VQ minus VP. What is the relative speed of separation? It would be the same as this one, so this is going to be 1.8. So we need to see where in this case it is happening. So obviously the the values cannot be very high. Values cannot be very high. So if the sum, so if the sum of the values is basically 1.8, that also means that the total momentum cannot be increasing also, because total momentum is conserved. So if you use this one, so total momentum before or after collision, momentum is increasing in this one, momentum is increasing in this one, momentum is increasing in this one, because either way you see the differences in the values over here, MV, the values are increasing. This is going to be correct because it has the same magnitude of values, and these are both in opposite directions. So relative speeds will be added the same way. So we said VQ 1.3 minus VP, so minus 0.5. So it will add up to be 1.8 also. So this D is correct. Okay, let's see some paper 2 questions also. Wait, I think we can do this. An object X of mass 0.3 kgs is traveling in a straight line at a constant velocity of 3 meters per second on a horizontal frictionless surface. Object X collides with a stationary object of mass 0.5 kg. After the collision, X moves with a velocity of 2 meters per second at an angle of 60 degrees to its direction before the collision. Object Y moves with a velocity V at an angle 41 degrees to the direction of X before collision. Okay. What is the value of V? Okay, so we are going to do the same thing as before. So before collision, parallel to X, that means this direction. You have 0.3 times by 3 plus 0. This is the total momentum before. Y is stationary, and there is no velocity perpendicular to this motion, so 0. But after there is. So after, like in the original direction of the X, you have V cos 41 mass Y 0.5 So 0.5 kgs times by v cos of 41. And now, as you can see, this one also moving in this direction. So this is 2 cos of 60, and x is 0.3. 2 cos of 60, right? And perpendicular to this direction, this is v sine 41, so 0.5 v sine 41 minus this time, because this is now in opposite direction, so 0.32 sine of 60. Okay, so we can basically see what's needed. What do we actually need to find out? We need to find out the v. What's v? So I think we can use either one of them, because there is only one unknown in both of them. There's only one unknown in both of them. So let's say, for example, we choose this one. You get 0.5 v sine 41 equals to 0.3 times by 2 sine 60. So v would be 0.3 times by 2 is 0.6 sine of 60 divided by 0.5 sine of 40. So 0.6 sine of 60, 0.5 sine of 41. This is 1.584. Let's see whether we get the same thing over here in this one also. So this one would be 0.9 equals to 0.5 v cos 41 plus 0.6 cos of 60. So this would be 0.9 minus 0.6 cos of 60 would be just 0.3, because cos 60 is just half, divided by 0.5 cos of 41. So 1.59 roughly again. So 1.59 for both of them. 6. Right. This is an interesting question, but this is okay. I think let's try some paper 2 questions. We already did this. Okay. State the principle of conservation of momentum. So total momentum of interacting bodies is conserved provided no external forces act on the system. Okay, so a ball X has mass 240 grams and moves in a straight line on a horizontal frictionless surface with an initial speed of 16 meters per second. The ball collides with a stationary ball Y that has mass 480 grams. After the collision, ball X is stationary as shown. Show that the speed v of the ball Y after the collision is 8 meters per second. Okay, so total momentum before, so total momentum before equals to total momentum after collision. So you have 240 times by 16 plus 480 times by 0. We don't need to convert this into kgs because all the masses are in grams, so all the mass values are multiplied by 10 raised to the minus 3. Total momentum after, so 240 will be times by 0 plus 480 grams is times by v. So as you can see, this goes to 0, this goes to 0, so v would be 240 times by 16 divided by 480, so times by 2, and 16 divided by 2 is 8 meters per second. Calculate the change in total kinetic energy of the balls due to collision. So first off, kinetic energy before, total kinetic energy before. So this would be half, and this time we need it in joules, so the kgs, 240 grams needs to be converted into kgs, and velocity was 16 squared. Total ek after, so this is going to be half 480 10 raised to the power minus 3 8 squared. So you have 0.5 times by 240 times by 16 squared divided by 1000. So this is 30.72 joules. This one. 0.5 times by 480 times by 64 divided by 1000. This is 15.36. So change in EK is going to be 30.72 minus 15.36. Oh, sorry, no. 30.72 minus 15.36. 36. So 30.72 minus 15.36 is equal to 15.36 joules. 15.36. So this would be 15.4, or just 15 also would be fine. 15. Yeah, two significant figures. Okay. The collision in B lasts for a time of 2 milliseconds. Assume that the contact force between the balls is constant during this time. Determine the magnitude and direction of force exerted in ball X by Y during the collision. So, during the collision, F would be, wait a second, total change in momentum for ball X by ball Y. So, change in momentum for ball X is mv, mv minus mu. So mv is basically 0, but mu was going 240 and 16. Okay. 240 times by 10 raised to the power minus 3 and 16. So minus just means in which direction it is happening, and then divided by time of 2 milliseconds. So 2 what is going on? This is 2 milliseconds, so 2 10 raised to the power minus 3. So as you can see, 2 10 raised to the power minus 3 will get cancelled. So you will be left with 120 times by 16. So this is 1920 negative. So this means that the magnitude is 1920, which is roughly 1900, and direction is towards the left. Ball X by ball Y. Towards left. Compare the magnitude and direction of force exerted on ball Y by ball X during the collision with answers in C. No further calculations are required. So they are going to be the same, but in opposite direction. So the magnitude of force exerted by X on Y is same as Y on X, but in opposite direction. This is a consequence of Newton's third law. You can also say that these are Newton's third law pair, action-reaction pair. Okay, alright, this one. State the principle of conservation. We have already done that. An object of mass 2m is traveling at a speed of 5 meters per second in a straight line. It collides with an object of mass 3m, which is initially stationary. After the collision, the object of mass 2m moves with a velocity v at an angle of 30 degrees to its original direction of motion. An object of mass 3m moves with a velocity w also at an angle of 30 degrees as shown. By considering the conservation of momentum in 2 dimensions, calculate the magnitudes of v and w. Okay, so motion perpendicular to motion parallel to original path. So that would be, wait a second, sorry, what was it? 2m times by 5 equals to, sorry, plus 0 equals to, because initially it was stationary, but now you have v, oh sorry, no, you have v cos of 30, 2mv cos of 30, and 3mw cos of 30. 2mv cos of 30 plus 3mw cos of 30, just to make sure that we have the right thing. So 3mw cos of 30, 2mv cos of 30, and this is 2m times by 5. Okay, and the motion perpendicular to original path. So there is no motion perpendicular to the original path before, but there is definitely after. So it's 2mv sine of 30 minus 3mw sine of 30. Now notice when you solve this one first, you get 2mv sine 30 equals to 3mw sine of 30. So sine 30 gets cancelled. So you get 2 is equal to 3w, or w is equal to 2/3 v, sorry, this is v. 2v equals to 3w. So you get V equals to 3 over 2W. Now we plug this over here. Again, mass gets cancelled. So we know that cos of 30 is under root 3 by 2. You can just verify right from the calculator. And if you're doing A-level maths, you should know the cos and sine tan of common angles. So this becomes 10 equals to 2 times by cos of 30. So 2 times by that. That just becomes under root 3 plus, 3b, root 3b. And then 3 times by cos of 30, that is this. So that is going to be 3 root 3 over 2 W. Now, when we plug V as 3 by 2 over here, so 10 equals to 3 root 3 over 2 W plus 3 root 3 over 2W. This simplifies to just 3 root 3. So 10 equals to 3 root 3 W. So W will be 10 divided by 3 root 3. So 10 divided by 3 root 3 brackets, so 1.924. And then when you multiply this by 3 by 2, or 1.5, you will get this. So 2.9 for this and 1.9 for this. An object of mass 4.2 kgs is traveling in a straight line at a speed of 6 meters per second. This is mass, this is speed. The object is brought to rest at a distance of 0.05 meters by a constant force. Calculate the magnitude of this force. Now, there are a lot of things you can do over here. One of them, actually two of them, involves acceleration, if we can find out acceleration. So we know this is U. U is 6, V is 0, S is 0.05. So we can find out acceleration. So acceleration is going to be 2as v squared minus u squared. The acceleration is supposed to come out negative, minus plus 0.05, and v squared, so this is going to be minus 6 squared. So acceleration will come out to be minus 36 divided by 2 divided by 0.05. So this is minus 360 meters per second squared. Now, if we have this, we can find out force by just doing mass times by A. Since even if it is decelerating, we don't care. We just need to find the magnitude of this force. So mass is 4.2 times by 360. This is going to be 4.2 times by 360. This is 1512. Another method involves the rate of change of momentum. So if we can find out the change in momentum, then we would need to find out change in time. So change in time would be v is equal to u plus at. Since we have already found the acceleration, you can find the time. If you haven't found the acceleration, then what you can do is use s is equal to half u plus vt to find out time. So time would be 2 times by 0.05 divided by u plus v, 6. So time would be 2 times by 0.05 divided by 6. So 1 over 60, basically. Let's stick to the correct one. Even if you find time to anything, you will be 60. So change in momentum is 4.2 v minus u, or just simply change in momentum, is 6 divided by 1 by 60. So basically 4.2 times by 6 times by 60. This is also 1512 newtons. This is method number 2. Now, third method involves the work done equals to change in kinetic energy, EK. So change in work done, or work done, is Fs equals to change in kinetic energy. Change in kinetic energy is just simply half mu squared, because v squared is 0. So this would become F half m, no, 2, sorry. U squared is 6 squared divided by S, which is 0.05. So let's figure out. So 4.2 times by 36 divided by 2 divided by 0.05, 1512. So either way, you're getting 1500. Right. Okay, I think we can call it a day over here. Hopefully this video was informative and simple enough. I hope the explanations were clear. If you have any questions, do reach out in the comments. You can reach out directly through any WhatsApp, email, anything as given in the link tree. Do check out the resources on Patreon. This great booster pack is amazing, especially if you are going to be doing MCQs, sorry, paper 1 in the coming few days. And yeah, so see you in the next video. Bye bye.